Okay, so good morning everyone once again, and welcome to today's session. Today we will be discussing the second part of statistical methods in R. Today we will be discussing more on the multiple linear regression and other general linear models and all. So we have already covered the regression analysis, basic statistical testings, and how to interpret the result, and descriptive statistics, and all those things we have already covered. And now we are moving to this one, like how we can simply do the statistical analysis and a multiple linear regression model. Okay, using R. Okay, so today, what we are going to do is we will be discussing about practical data. So first of all, let me load the data first. Mm, So, as few of you might be aware, like we do have a option in R, like we can import the data using the reader package, and we can import the data directly from the source code itself. And also we have an option that is called import dataset here. So from here also we can import different type of data. So if you look here, we have two options to read data from base R and using read R package. Okay, so as I mentioned earlier, we prefer to go for read R option because read R will give us some more of better control over data frame, like it was loading the data as a table format. So it will be more faster, and also we can prefer to have this one. So I'm just taking the reader format. Okay, so if you have SPSS data or Excel data and all, uh, yeah, these data you can actually take the data from this one itself. Now, I'm just taking an CSV data, as I have a CSV data here. So from text, and I can just browse the data. So here, this is the student performance data I have today. Okay, so this is how we can load the data. This is the data is actually loaded here, and we are getting the code as well here. Okay, we are getting the code for the data set also here. So any adjustments we can actually do it here. Any adjustment and the data and all we can simply do it here, and also like we can rename the data set like student performance. And now it is student performance. Let me do we need to rename this one? Let's put as data, or okay, I'm just taking it as data 2. Okay, just for a simple purpose. And if you need, we can simply update any of these parameters and all. If I need to skip any rows from the data observation, I can simply do it as well. I can skip a number of rows, so it will be skipped from the data. And here I can check first row as names, so it will be consider the first row as column names, and delimiter is, as it is a CSV, it is comma separated only. And then trim space and all, any comments and all. So so those kind of things, what are the comments in the data, so we can choose the symbol which is actually used for comment. And any NA and all, what is the representation of NA values here. So so we are keeping the default. If needed, we can actually choose those things as well. So here some NA values might be there, but we'll see. Okay, so with these things actually we can import the data, but rather than importing this data in this window, what we can do is, it's a better option always, just copy the code from here. So here whatever update you are making here, that will be implemented here as well. The code will be updated. So here I changed the data set name, so it is actually updated here as well. Now I'm just importing the data. Okay, so instead of importing, I'm just copying and cancel this one. So here, um, in the script itself, I can update those things. Like first one is multiple linear. Okay, and yeah, so okay. So I just copy the data set like this, and copy the code like this. Now I'll mention the question as well here. So here we are actually looking at a student's performance data. Uh, okay. So here let me okay, before that let me put a description about the data set. So or I think uh, okay, I think we can go with one RMD file, so that where you can actually have bit more clarity on that. So I'm not going for R Markdown. So we'll be going with Corto. So Corto is an advanced Markdown format. So it's actually very advanced, and it is offering a lot of new features and all. But yeah, it's works similar to the Markdown only. So I will just use this one. So students performance multiple linear regression model. So okay, okay, I'll keep my name as well. Only take HTML from here. Yeah. So I think okay. So I'm getting this one. So let me save it as multiple linear regression analysis. Okay, so I'll be save it as multiple linear regression analysis. So I'm getting some us in this one R markdown. We are getting some sample codes as well. So I'm just skipping those things, and we'll add some basic things about the data set and problem. Okay, so okay, so this is a sample here. This is about the data set. Okay, so this is a student's performance data set, and this is designed to examine the factors influencing academic students' performance. The data set consists of 10,000 student record, which each record containing information about various predictors and performance indexes. Now, the variables are here like hours studied, total number of hours students studied, previous score, extracurricular activities, sleep hours, and sample question papers practiced. Okay, and target variable will be performance index. Okay, so performance index is a measure of overall performance of a student. That performance index represents the student's academic performance and has been rounded to the nearest integer, and the index range from 10 to 100, with higher values indicating a better performance. And this data set aims to provide insight to the relationship between the predictive variable and the performance index. And researchers and data analysts can use this data set to explore the impact of the study hours, previous course, extracurricular activities, sleep hours, and sample question papers on students' performance. So this is the data set we have. Now, the code we have already imported to load the data set and this one. So we can simply copy the same code um, here as well. So I'm just taking the chunk here. So for creating the chunk, we can use the control alt and I. So that will give the chunk here. So I'm loading the necessary libraries and all. So let's keep that is outside this one. So okay, we can keep it in heading 2 level. Okay. Then we'll be having an option to load the data set as well. So we'll just take the data set as well. Okay, another chunk we can take data set. So control alt and I, it will insert a chunk, or you can insert the chunk from here. Okay. Uh, okay, here. Okay. Let it be the second heading. Okay. So this is also I'm changing to a second level heading. Okay. We can either use the visual options here, or we can simply use the source option here as well. So why I'm keeping the load libraries as a separate chunk instead of keeping everything in a one chunk is, so while using a professional programming approaches, we usually keep the necessary libraries loading at the beginning. So that will help the programmer to understand what are the libraries needed and load the libraries in the initial stage itself, rather than getting some errors while working with some other part and all. It will be easy to load the libraries and all. And so every time it's a good practice to keep the load libraries chunk if you're using RMD, or if you're using a program also. Just keep a loading necessary library part at the top. So, and load all the libraries, all the packages whichever is needed throughout the program at the beginning. Okay. And for example, if you're going to some 10th row and all, and then you are seeing like okay, now you have to load some package called deep layer. So just add it in the top rather than adding it here. Okay. Now, okay, so now this is the data set. Let us load the data set as well. So I'm loading the libraries here. Now loading the data set. So this is the data set we have. Excuse me. So this data set tells us like these are the parameters we have. Okay. So these are the variables we have. Our studied and previous score. Our studied previous score, extracurricular activities, then sleep hours, sample question papers, practice, performance index. These are the parameters we have. Now, okay, okay, these are the parameters we have, and now we need to change like okay, what are the values here? So our studies is a numeric one. Previous score is also numeric. Extracurricular is kind of a factor variable. Currently, it's a character variable, I think. So it's left aligned. So it's a character variable. Sleep hours is numeric. Student sample questions practiced. That is also a factor one. Sleep hours also we can Okay, that is let it be a numeric one. It's hour. Then performance index, it's definitely a tag as it is target variable, it will be definitely a continuous variable only. Okay, so that is about the variables. Now this is our data. Now, so we have loaded the data set, and while using the read CSV function, so we are getting this things as well. 10,000 rows and 6 columns are there. Delimiter is comma. Then one character variable is there. 5 numeric variables are there. Okay, this is the character variable, and these are the numeric variables are there. Okay, so now we have this one. So I'm just commenting out this part, so we don't need a to view the data. So I'm just putting spec function, spec of data too. So that will give me the specifications of the columns here. So these are the column specification. Okay, and this is the column specification for each of the data set. So I'll go to the source itself rather than using this one. Okay, so spec will display the specification of the data set, and str will display the structure of the data set. So data structure will be like this, this is a table, and 10,000 into 6. Okay, so 6 rows are like this. So first one is a numeric, that is 10,000 values are there for all. Previous score, extracurricular activities, sleeping hours, sample question papers, practice, performance index. So with reader format, like we are getting the tuples and all. So there, what is the advantage is like we will be getting a sample here as well. Okay, so uh, some of the data set values will be displayed here as well. Okay, so we can see a data structure here. Uh, okay. If needed, we can also look at the glimpse of the data. So here, glimpse of the data also shows us the same. Okay, these things only. What are the type of character, type of variable and all we will be getting here. Okay, so any questions here? Okay. So we have loaded the data set. So yeah, now we have the data set. So and with all the attributes and all, I'll just paste this thing. So now we have import the data set, and it looked like the shape of the data set as 10,000 comma 6, which is 10,000 rows and 5 sorry 6 columns as a matrix format. Okay, so target variable is performance index, and the remaining 5 variables are independent variable. There are multiple independent variables, so we can perform the multiple linear regression model here. Now, so okay, now we can actually perform this model. So before that, we need to convert a couple of the variables into a factor or integer and all. Okay, so first thing is okay, so Okay, so variable conversion, we have these three variables like mm, data to extracurricular activities we can convert to factor variable, then df dollar performance index, we can convert it into integer, because they also mention like in the data set, they have also mentioned it will be rounded to the next integer value, so we can simply convert it into integer value as well. Okay, so that is there. And okay, these are the two conversions we can do. Okay, it has already extracurricular activities. Okay, okay, it's not dot activities, so that's why. So if you have a column with a space in the column name, you need to put this symbol uh, to make sure it is actually considering as a column with this one. It means it is actually reading the column properly. Okay, so similarly for performance index, we have this one. So you can see it here. While displaying the column name, it is actually displaying like this, as it is having a space. Otherwise, you need to okay. Otherwise, you need to put it in the square bracket, and in inside quote you need to prefer. Okay, inside quotes you need to make sure this is actually here. So I'm just running it again. Performance index closure is not subsettable. Okay, what is that? Okay, it actually changed. It's data too, sorry. Okay, so it is actually converted now. Now, if we keep the column names like this, it will be difficult to everywhere we can mention the column name. So, rename the columns uh, using dot instead of space. Okay. So we'll be renaming the call names. So we'll be using the gsub function rather than taking every columns and every column names and updating it. So call names of data two, that will give us the call names. So this is the call names we are getting. So gsub function, this is actually for a regular expression, or we call it as regex. Okay, so okay. Okay, so we are actually changing the columns using regex method. So that is the short form of regular expression. So where you are using Python or R and all, you might be familiar with these things. This is actually the using the regular expression format. So here, what it is actually using is this is actually substituting. So it is finding the pattern of space in the times and replacing that pattern with a dot. Okay, so it is applying to the column names of data 2, and once it is updated, we can see the column names once again. So here, yeah, now you can see the column names are restructured like this. Okay, so here we had a difficulty, like we need to put it in this format, so that will be difficult going through all the variables again and again. So we will be simply changing that attribute like this. Okay, now Now we will see, we have loaded the data set and make some changes to the data set. Now we will see the summary of the data set. So for summary statistic, we can simply use the summary function. So it will give you the summary statistics of the data set. So if you look at the summary statistics, so here we have already converted that extracurricular activities to numeric. So we are getting the numeric summary, so factor. So we are getting the factor summary here. And for this other variables, we are getting the numeric summaries. As these are the numeric variables. So here we can see number of hours studied. It is actually from 1 to 9 hours with a median of 5, which is good. Actually, kind of normally distributed data from here because it actually follows somewhat a normal trend. Okay, and here it is previous course. It's starting from 40 to 99, and that is with a median of 69. So kind of a bit skewed data. So then when we come to the sleeping hours, it's starting from 4 to 9 again. Then there the median is 7, and this one. So here also it's a skewed data. It's not a normally distributed. Sample question papers practice, that is varying from 0 to 9 with a median of 5, which is actually kind of a normally aligned data, um, with a small change in the center point. Okay, then performance index. So here also the data is starting from 10 to 100 with a median at 55. Uh, so that is giving a trend like okay, all the students are having a normal trend regarding the performance index. So basically, the summary statistics actually gives us some ideas about the distribution of the data, and distribution of the data set, and then we'll be getting some insights about the quartiles, and also overall summary we are getting. It's not some numeric values like this. From these things we need to obtain the data flow and all, like what is the type of data or how it is actually fluctuating and all, how the data is moving, what is the distribution of the data and all. So I need to know all these details as well. Now, okay, now we will be checking for the missing values. So, for missing values, we can simply use the call sum of is dot na of data 2, and okay, I think typing data to also okay, typing data to also will be having some issue. So I will just change the data to data, or let's put df itself. Okay, so that will be easy while typing. Okay, so I'm just changed everything to df. So I'm just running every columns until here. Okay, so all the columns are run, and call some of the data. So it's showing there are no missing values in the column. Okay, now no missing values found in the data set. LB put that statement. Now we need to check if any duplicate records are there in the data. So okay, so for duplicate row, we will be using the duplicated function, but we wanted to know the sum, so we will be using any function. Okay, um, we can also check the sum of this one, but for before that, we can see any duplicated records are there. So if any duplicated records are there, then only we need to yeah, and then only we need to check at the sum and all. So any duplicate records are there, that is actually true. So there are duplicate records. So we can see the sum of the duplicate records. Okay. So there is 127 duplicate records are there. So we can simply check those duplicate records. Okay. So there are duplicate records, that is throughout the values having throughout duplicate record. So we don't need that duplicate record. So that might be impact our analysis. It might be from different students, but actually here we don't have a student ID and all. So we will be considering it as individual results. So in that case, actually we are not sure about those duplicate records. So in that case, we will be um, removing that data set. So we will be reframe the data set. Let's say df1. That will be, we can either take the sorry we can either take the data set like this. Okay. We can either do the duplicate like this, removing the duplicate, and if we check at end rows, okay, so it will give you the unique rows only. Also, we can also do this in a simple format, like df1 will be equal to like unique function. Okay, using unique df, we can also take the unique data frame. Okay, so I'm just commenting this one, and I'll be using the unique function. So that is actually more simple while doing the coding and all. Okay, now we'll be checking the summary again. So because after removing the data set, we'll be having some issue, some changes, like we have, okay, okay, this is actually applicable in the top. We'll calculate the summary statistics for new data set also. So that will be changed because um, there is a change in data set. Almost 1.2 percentage of the data is changed. So there will be a change in the data set also. So we will be checking the summary statistics again. It's not much affected, but yeah. There is a slight variation in the mean and all, but median and all mostly stays the same. Okay, now we now we have the extracurricular activities and all, so we can see how that is actually performing. So okay, so we will be checking the frequency of extracurricular activities first. So that will give you the same table. So this is the frequency of extracurricular activities. We can also plot the extracurricular activities using a bar plot. So we can simply use the bar plot function. Okay, so that will give you the plot of extracurricular activity here. Okay, so this is the extracurricular activities with the frequency distribution. So this is the frequency distribution of extracurricular activities. Um, Now we can also table some other values as well. So here we've seen the frequency distribution of extracurricular activities. So we can see the frequency distribution of hours as well. Okay, we can see the frequency distribution of hour variables as well. So we have two hours variable. So okay, that we can see later. But first we will see the frequency distribution. So here we'll use this table function. So table of df1 hour studied and table of df1 dollar sleep hours. Okay, so these are the two hours variable hour variable we have. So we will just find the frequency of those things. So here, okay, okay, so this is there. So now you can see here it is actually coming like this. So we can actually do one thing. We can do the cat function here. So cat function will display this thing instead of yeah. So it will display the comment as well. So here it is showing frequency distribution of hours studied. So instead of simply putting a comment, we can do it like this. So cat of this one, so it will simply show you that this things this heading as well. So cat, okay, uh, okay, so I'll be putting this way. mm, okay, so let's keep this inside. Okay, so there will be a space as well. So here you can see um, no, it's sleep hours. Okay, so here you can see it is actually the frequency distribution of these two things. So like this, we above also we can put the headings as needed. So the frequency get, okay, so we can put this thing. So it will show the frequency distribution of extracurricular activities. So this is actually helpful when you are actually using the you are using the R markdown or Corto function. Okay, so this is good. So we have seen the extracurricular activities, sleeping hours, hours studied, and all. So their frequency distribution is like this. So most of the students are having some similar kind of sleeping status varying from 4 to 9. And yeah, here our number of hours studied also having some kind of a unique trend throughout, except from 1 hour study people and uh, 6 hour study, 6 and 7 hour study people. So they are having a slightly varying one, and rest of the having a more common kind of similar kind of hours. But everyone is having a more kind of closer numbers with every hours. Okay, so here now this is actually there. Now we can see the histograms as well of these. What is the run button here? Okay, so we will see the histograms of um, each of these things. So here you can see histogram of our study. So it's almost same throughout this one. Okay, now we can put all these things in a box plot. So that will help us to understand the um, trend if they have some outliers and all. So for that actually we can put we need some other libraries as well. So I'm checking it. Yeah, I'm taking the libraries dplayer and ggplot2 as well. So I'm running it again. Okay, now I'll go to this part. Okay, so here, okay, I'll be taking the distribution plot. That is what we have covered. So we will cover take the box plot for numeric variables for checking outliers. So that will be like we can. Okay, we can put multiple box plot in similar one. So like this. So I'm just taking df 1 hour studied. So all these variables I am taking together, and then main heading will be box plot for numerical variables, and names will be as like this, and yeah, so colors will be like this. Okay, so these are the colors, color scheme and all. So I'll be having this one. Now let me run this one. So here it is actually showing the box plots like this. Now you can see here it is actually affected with previous core. Previous core is having some. Okay, this is actually too much. The name is too much, so it's not displaying here. So I'll put it as questions practiced. Okay. So here you can see it is highly affected due to the previous score. So we can skip the previous score and take the other variable. So we will be getting a cleaner view. So okay. So I'll be taking this without this previous curves. So I'm just removing that previous curve from here as well, and just changing this color as well. Okay, or I can put a new color schemes, that is okay. So here I can put a mm, different color scheme, and let's put a border as well. Sorry, border equal to black as well. So what is the no repeater? So here 1 2 3 sleepers. Data, dear phone, hours studied, dear phone dollar, sleep hours. This one. Mm, we have 12 hours, so I'm just putting 13 here. Let's see if it is actually no. Here it is actually. This is okay. That is also okay. So then where it is actually having issue? Okay, so here it is okay. There also it's okay. That is also okay. So it's a sit with color. Mm, okay, in color it is actually showing something. Color. Oh, okay, 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 okay. So sorry. So got it. Got the problem. So the problem is actually color I didn't put. Okay, color equal to I didn't put. That's why it's actually it was showing some issue. Okay, sorry for that. Uh, color equal to still having studies names. Oh, okay, comma. Okay, so now we have the box plot for these three variables. This is more kind of a similar aligned. Okay. Um, okay, now we have this one. Okay, so we'll put x as variables as well. So here we have the plot. Okay. Okay, now we have this plot and all. So here we have this plot. So here we had this things, and now we will check also for the previous core and performance. So that is having the values similar. That is having similar values like from this one 0 to yeah, that is having values from 10 to 99. So we will be checking that as well. So okay, so okay, so this is the code for the other one. So we will be having outliers for previous core and performance index as well. So this is actually the scores. Okay, now from these things we can ensure that it is not having any outliers in any of the plots. So outliers is not there. So it's not showing any outliers. So we don't need to dig into the other things as well. Now we already plotted the bar plot for extracurricular activity and all. So we can also we have done the extracurricular activity plot somewhere here. Yes, here. So this is actually the plot we have created. You can also create this extracurricular activity plot in different way as well. So okay. So now we will be plotting the extracurricular activities data as well. So for that we can use this one. Okay, now here what we are doing, first one is we are just creating a data, plot data that will be okay, so it should be extracurricular dot activities. So let's put that. Okay, so we'll be having this data. So plot data will be like this. So extracurricular activities and the corresponding n values we will be having. Now we are creating a bar chart for counting extracurricular activity. For that we are creating ggplot. Data we passing. Axis we are passing. X will be extracurricular activities column, this column, and Y will be this count. Okay, n. Now we will be using the geom bar and filling with black and color will be black and fill will be steel blue. Then identity is the stat because we need the exact count like this only. Then width will be 0.5, so we can adjust the width accordingly. Also we are putting geom text. Axis aesthetics we are putting the labels, that is n. We are putting the n there, and we we are putting this 2 and color will be white for that font. Then label also we are putting. Then we are displaying plot as well as the data. Okay, so once we run in this one, we'll be getting the plot here. This is the plot, and this will be the data. Okay, now we can also update the themes here as well, plus theme minimal. Okay, so we'll be having a minimal theme because I personally don't like this gray outline for the plot and all. Okay, so that will be the plot. Now we can convert the extracurricular activities and convert. Okay, we can convert the extracurricular activities to numeric, and we can just do a plot. So okay, we can. Okay, so here we are just doing this one. So I'm putting a extracurricular activities dot number. So I'm creating a new column, extracurricular activities dot number, and here I'm using the if else condition. If df $1 extracurricular activities is yes, then 1, otherwise we are putting 0. Okay, so this is the update we are making here, and we are just transforming this data to um, a longer format for we can. Okay, mm, okay, so here. our study previous score, sleepovers, sample question paper practice, extracurricular activities. Okay. Okay, names to variables and values to values. Okay, let's put this one. Okay, here one more thing we need to do, that is actually we don't need that extracurricular activities thing, so we'll be removing that one because that is already considered in numeric format. Sorry, uh, already considered in numeric format, so I'll be removing that one. Select sorry. Okay, so this one I am removing here. Now, after this, my head of long data will be like this. Mm, unused argument 0, if else unused argument 0. So why it is unused? If else TF1 and all extracurricular activities. Yes. Why it is unused argument 0? Okay, here. Okay, so here we are checking the data. So this is our new data with the new variable, numeric variable, and this will be our new this one. Okay, so based on performance index, we can actually see what are the variables what are the variables, how it is affecting. So longer data. So this is the longer data, and based on the performance index, it's actually sorted the values. Okay. Um, we can also arrange it in. Okay, we can also arrange. This is actually not arranged in an ascending order. We can also arrange this one. So arrange by performance index. Okay, we'll be arranged it using performance index. So okay, now the data will okay. It's actually we'll arrange it in descending order. Okay. Okay, so this is actually arranged in the descending order. So who is having performance index 100? Actually, they are studying for 9 hours and having 98 score previously. Sleep hours same. Sample question, most of the sample questions they have carried, and they are working with some extracurricular activities and hours studied and all. Now, so we can why we have created this is we can plot these things using the respective features. We can plot uh, with this one. Okay, so first we will do a pairwise scatter plot. So that will show the relationship between each of the variables. Let's put 1, 2, 3, 4, 5, and performance index. Okay, so here we will create a pairwise plot. Okay, this is a pairwise scatter plot for each of the variables. So it is very it's not actually giving any patterns and all. So we can do one thing. We can plot the respective features at the target columns as well. So we'll be doing that one now. So okay, for that actually we can do a simple R code like a simple ggplot for pairwise understanding. Okay, okay. So here, mm, matrix, okay, matrix values. Okay, so okay, now this is actually the pairwise regression, like pairwise plot showing the linear relationship. So extracurricular activity, that is a factor column. So it's actually not having a linear trend. So other things you can see a linear trend over there. So previous score is actually linearly depend to the column. Okay, it is actually having a good collaboration with the performance index. So you can see that. And here, sample question papers and other factors are having not a much relation to the variable, but these two, our studied and previous code, this is actually having some linear trend, mostly some linear trend it is following with the target variable. So this is also one way we can represent the relationship before going with the regression model and all. So we can plot it using this method. Okay, so this is also a method we can do for plotting and all. Mm, before we started with the regression analysis and all. Now, now we can check the correlation plot for understanding the correlation metrics with okay. For correlation plot, we need a library called corplot. So I'll be adding that library here. Let's put the library. Oh, sorry, library here. So we need a library idea library sites and all we need, but here now currently need core plot only. Yeah. Okay. So these are the libraries. Let's load this and let's see if it is not there. Okay, it's not there. So you can install core plot. This actually gives a nice correlation plot rather than just having the metrics and plot it. Okay. Now, okay. Now first we will remove the okay. F- okay, we will only select the needed variables, like we will be removing the extracurricular activities column. So we will be keeping the other values only. Now we will create the correlation matrix. Okay, so yeah, this is actually the correlation matrix with the selected columns only. And now we will create the correlation plot using this method circle. Okay, and okay, with method circle we will first we will see the correlation plot itself. Then we will add more features. So let's run this thing here. Okay, so here you can see the correlation plot with highly correlated values are in circles and less is actually faded one. So, but here you can see one problem, that is actually mm, these variable names are too high. So we can actually rename the variables. So I'll select correlation data. So df1 and I can use a select function. Okay, so I'll be selecting these variables only. Our studied previous go, sleep hours, sample, question paper, extracurricular activities, numeric, and performance index. And okay, so here instead of selecting all these variables, what we can do is we can simply eliminate this variable and keep other variables. Okay, so that is a better approach. So minus this one. So that's a one line of code, and rather than selecting with all other variables. So here I forgot I equal to assign. Now I can rename these things like core data. I can rename these variables. Um, okay, activity is equal to this one, and uh, performance index. Then something our study our. Okay, we can rename the variables like this, and now we can change the correlation matrix simply using the correlation of this data itself, correlation data. So we don't need much decorations there. And now we can just plot it once again. Uh, where is extra calculator? This is there, no? Oh, okay, okay, okay. So it's actually core data. Sorry, forgot that. Okay. Okay, so here you can see these are actually updated with this thing, and we can also get the correlation matrix as well. So here we can print the correlation matrix first. Okay, so this will be the correlation matrix and this will be the correlation plot. Okay, here the correlation is very high. So what I can do is I can display it with a round function. So round correlation matrix, and I can put it into uh, digit 2. Okay, 2 digits. So it will be a neater version like this. And correlation plot, we can do the plot like this as well. Okay, so here we have this one, and here is the plot. Now we can actually make it better, even better. So with the update, so I'll be using this code so to give a better plot rather than this one. So here, mm, correlation. Okay, correlation matrix. So now you can see this is a little more neater version, having the variables neatly arranged. Okay, so this is one thing, and now we can do one more thing, like so we have checked the correlation and relationship of a linear relationship of the features, and then we have checked the correlation. We can also okay, we can also check if the variables having a normality and all with the target variable. So first we can do the normality test. So that is actually using Shapiro test. We can do the normality of target variable. Um, okay, so once we do this, we will get the mm, okay. So won't accept this thing. Okay, okay. Sample size is greater than 5,000, so I think this won't work. So what we can do is we can do a plot instead of this with the other variables. So okay, so we can do one thing is we can do df1, and instead of hours studied, we have hours dot studied. Okay, and Okay, so here what we are doing is we are using a ggplot because Shapiro test is not suitable for a variable having greater than 5,000 sample size. So we are doing a ggplot with each of the variables, the feature to make sure the features following somewhat normal distribution. So here P1 will be first plot, that is ggplot2. We are doing taking the variable, then giving the axis, so aesthetics, like we only passing x-axis because for histogram we only need one axis. So here geom histogram we are using, and we are adding the second axis after stat density. We are taking 30 bins and filling the sky blue color. And stat function we are doing here is actually we need to we are actually integrating the stat density plot also here in geom histogram. So that's why we are keeping the statistics functions as well. Function d norm normal distribution normal density arguments we are creating. So here we are giving list mean of this one and standard deviation of this one, and based on that we are putting that in dark red line. Okay, so we are plotting that one. So it will be a plot like this. So here the normal density is also incorporated along with the histogram. The normal density is also incorporated. So here we have 30 bins. We don't need a 30 bins here. So let's take 10 bins here and see, because with 30 bins there are a lot of gaps are there. So with 10 bins also there are one gap. So let's keep 9 bins. I think it will fit somewhat. Yeah. So we are having a plot. Now let's put a theme minimal as well. Okay. So or we'll do the classical theme. Okay. So classic theme will do. Okay. So this is the classical theme and incorporated the values. Okay, densities. Okay, so it is actually incorporated here. Okay. Now what is your call here? Like, is it following normal distribution or this one? Okay, I think now we will do the similar thing for other variables as well. So here it is somewhat following a normal distribution. It's not exactly normal. Yeah, but we'll see other plots as well. So let's see. Here we have taken the hour study. So now we'll take some other variables. Um, let's take previous score, how it is impacting. So I'll be changing it with these variables here. And instead of rag and dark red, we can put brown. Okay, so it will be P2. Okay, so that is also kind of similar. Now we will create one more here, that is with the performance index. We can see performance index. So P3, P3. Okay, so P3 is performance index we have added here, so that is also fine. So these are the things we have already got it. So here we got these things. So now we are ready to go for the so Shapiro test actually we have tried, but the thing is we only need the target variable, but while doing the Shapiro test, we will be getting an error like it should be less than 5,000 sample size, otherwise Shapiro will fail. So I'm just commenting this one for okay, I'm just commenting this because it's not applicable. Okay, here. Now we will move to the regression part. So here we have taken the data things and all. Now we will move to the regression part. So let's put the model first. Now, so first we will fit the multiple linear regression model here. So model will be using LM function. So so instead of giving all these variables together, we can just put this one itself, comma, data equal to I can put df itself. So data frame itself, I don't go for dm1. So let's keep the summary of the model and see what it is actually explaining. Okay, so here we are getting this. This is the formula we are getting. Now we can explain this thing. So from residuals we can start. So the residuals which is actually having a difference between the observed and predicted value ranging from this -8 something to 8 point something. Okay, so this is the residuals are actually moving, and the first quartile is minus 1.36 and median is minus 0.30 something. So it's kind of a little skewed. Okay, from the data it is a little skewed towards left. And these, but it is more close to the zero and all. And so it is, we can say it is relatively a symmetrical distribution around zero. There is a slight deviation, but it is relatively normally distributed, relatively normal. Okay, we can say it relatively normal. It's not exactly normal, but relatively normal. For practical data, we will be only getting those things. Now here, intercept value is around minus 34. Uh, that can be as we discussed yesterday, it is actually again some hypothetical situation. If all other values are zero, the score is minus 34. So our performance index is minus 34. That is not a what factually it's not correct in a real scenario, but sometimes it actually happens. So it's not having that much significance. So we can keep it on hold. So it represented the hypothetical performance index when all the performance indicators are actually zero. Okay, so that is not going to happen, or we don't need to have that one. So let's keep it there for the model purpose. And when it comes to the other factors, all the coefficients are positive, all the coefficients are positive. And other so all the other variable indicate all the other variables tells us that while they are increasing, okay, each of the variables increasing, there is a dependency on the performance index as well. Okay, so all other variables indicate that increasing those factors are associated with an increased performance index. For example, if hour of study, 1 hour of study is increased, then performance index will be increased by 2.8542 percentage, okay, or times. So that is actually the interpretation of this one. Here you can see two of the variables is actually having some higher estimate or coefficient values. So we can say that these two, our studies and previous score, these are the more influenced points. This is actually clear with this plot as well. So here you can see these two are having these two are actually showing a linear relation, linear trend here, and a previous score is highly affecting the current score or performance index as well. So, and correlation also, previous score is actually having a high impact, and our study is also having a higher impact on the performance, you can see here, okay, compared to others, okay. So yeah, that is one interpretation. So, and all the p values corresponding to these coefficients are actually statistically significant. It's less than 0. um, it's highly significant, so as we discussed yesterday. Now, high R square here. Here we have a high R square. Adjusted R square and R square is very high, like 0.988. But in some cases, we call it as overfitting. It's actually very close to 1. Now, this high R square indicated like a very strong linear relationship between the independent variable and dependent variable. Um, so the model is actually explaining uh, all the variables are actually explaining the performance index well. That is what this R square and adjusted R square says. And F statistics value also, it's very close to 0. Uh, and p value is also very close to 0. So that is actually highly significant, that confirm the model significantly explain the variation in the data. So overall, the model is actually appearing well fitted one, and all good. The model is actually performing well. Now we can do the regression diagnostics as well. Um, so we'll plot this one, diagnostic plots. Okay. So why this par m fro is actually it is showing we need a 2 by 2 plot, because every time keep in mind, like a regression model will show you the 4 plot, that is, one is residual and fitted plot, then normal QQ plot, and scale and location plot, then the residual was leverage plot. So these 4 plot it will show, so we can actually show it in 2 by 2. So that's why we are putting the mf row 2 by 2. Otherwise it will show 1 by 1, the plot 1 by 1. We can also show it like that as well, like this as well. So it will show individual plot, but that is not necessary at all, so we can keep it this. But once you completed that, make sure that you give this one back, so otherwise it will show other plots as well in that format. Okay, so now here the QQ plot. Okay, so first one is residual and fitted plot. So if you look at the residual and fitted plot, it's actually the random scatter around 0, like um, here it is not exhibiting any constant patterns and all. So and there is no underlying trend and all. So it is okay. But when looking at the QQ plot here, which is more important, the QQ plot is actually mm, it's almost close to the diagonal, apart from in the tail ends, both the tail ends. So it's almost very good. indicating that the residuals are normally distributed. Okay, so overall, the model is actually good. Not having much issues in the model, and so it's almost randomly scattered around zero, we can say, and significant. That is significant and a good part to the model. And errors are also unpredictable, and model's assumptions about the residuals are likely meet because it's not all close to the zero. It's actually scattered bit. So, mm, but overall, the model is actually good. Um, Now we will see the VAF also on the variance inflation factor as well. So, so for VAF we can use the library car. So I think we didn't use that one, so we will keep it in the top. So whenever libraries are needed, we need to place it here only. So okay. So this is the VAF values, and this is the values for each of this one. So all the values are actually close to 1, as you can see here. So so if the value is 1, it actually says that there is no or less multicollinearity. It is actually slightly deviating from 1, so it's showing a very less multicollinearity. So VAS value normally, it actually depends. Some cases, like it is actually said to be we need a VAF value less than 2, but in most of the practical situation we consider the VAF value between 1 to 5. That will be considered as okay. But if the VS value is more than 5, it is considered to be there will be multicollinearity. But in some areas, like for example stock market or this um, crypto market, and also for those kind of analysis, financial analysis and all, or if it is a pharma analysis, and also there, um, there it is actually said to have the VAF value should be less than 2. Okay, they are actually taking it very seriously, so it should be very 2, less than 2. Okay, so that is about the VAF thing. Now we can actually test the regression model. Mm, okay, so first we will test the regression model using ANOVA. So okay, so here is the regression model test using ANOVA. So here everything is having a degrees of freedom 1, and okay, so here, okay, we are actually bit over the time, so it's almost close to 2 hours, right? So we'll keep a break after explaining these two things, testing and this thing. Okay, so okay, so first we will explain this ANOVA model. So here you can see, as we saw this model yesterday in the ANOVA model yesterday. So here, mm, here we have tested all the predictors together, significantly explain the variation in the performance index. Now, okay, so ANOVA is actually so most of the time people are not using ANOVA in a regression. So, but ANOVA can be used in a regression as a significance test. It's not a group comparison like we did do for the normal ANOVA. So um, here we have predictor variables, hours studied, previous score, extracurricular activities, sleep hours, and sample question papers predicted. So these are the variables we have. So here each of these parameters actually explains like each of the variable explain and the significant portion of the variance in performance index. Okay, so here all the variables are having a value less than in 0.5. So that means it is actually mm, it is actually having a significant portion of variance in performance index. Okay, that is the overall conclusion for this analysis. But now you can see a couple of things. So here we have degrees of freedom for all the variables are 1. That is because it's a numeric predictor. It is not taking all the individual observations in the variable. So it's actually only taking it as 1. The only thing it is actually taking is residuals. That is actually having the rest of the variables. Okay, so this is actually because of the large sample size, that is why it is showing the higher residual higher degrees of freedom in residuals. It's mostly depending on the residuals, not on independent variables. Now if you look at the sum of squares, like here previous score and how studied, that is actually showing a higher significant value. So we can actually keep these two values. Okay, these two factors are actually more contributing towards the model. So here previous scores actually explain the largest chunk of the performance index, and uh, and this will remain the strongest predictor variable in the model as well, followed by our studied. Okay, then the f value and all is actually we have a higher f value for these two variables, and which again gives the significance in the import significance in the model. So based on the f statistic we can arrange the significance of each of the variables. Like first one will be this, second one will be this, third one will be this one sleep hours, and fourth one will be sample question papers studied, and fifth one will be extracurricular activities. And all the p values are close to 0. That is that every variable is contributing significantly. None of them need to be removed from the model and all. So that is the overall model. Mhm. Okay, so that is what actually this ANOVA says, and it actually confirms the significance of the regression model we have created. Okay. Uh, Now we can predict new values. Before predicting new values, we can test the values in sample. Okay, we can take a sample because we didn't take any test data set, so we can take a sample and um, we can create a sample data. So sam data uh, that can be, I can create a sample df1 comma, I can take 100 samples, and let's predict on the 100 samples. So we don't need to replace the value, so replace equal to false. So Then we will predict the, using predict function, we will predict the model here. So let's predict the model. Okay, so we'll predict the model within the new data. So um, okay, and sample data performance index, or we can do it in this way. Data dot frame. Okay, so round predictions to 2. So I'm just creating the predicted data set like this, and okay, taking the head of predicted. So here what I'm getting is the actual value and the predicted value. So you can see it is mostly close values, apart from some lower values. It's performing close to the actual values. So we can see the other performance indexes and all. So now we can find the RMSE and MAE values. So RMSE is the mostly used method to um, calculate the performance inside the model. So RMSE will be square root of mean of the difference between predicted and actual and predicted square. Okay, so that will be RMSE, and okay, we will calculate before RMS, we will calculate some other values. Mean absolute error we can calculate. So this is the mean absolute error. Then, okay, I'll type it. Uh, okay, this is mean absolute error. And then we can calculate mean square error. That will be MSE, mean of this predicted actual and predicted square. Then we have this one RMSE, so that will be root mean square error. Okay, so square root of basically the square root of MSE. So, but we can also calculate in this way as well. So, okay, mm, okay. So these are the matrices we have. Mm, so mean absolute error is 1.41, and mean square error is this one, and root mean square error is 1.78, which is very good here. And also we can calculate the R square value also once again from the model. So I'll tell you how to calculate a R square value. Uh, Okay, so for that we can calculate the SST and RSS. So that is the ANOVA values you already know. This is residual sum of square and total sum of square. So that is sum of actual minus predicted. The mean. This is the formula you already know. So R square will be 1 minus SSR divided by SST. Okay, so this is the R square formula. So we can also print that one. Get R square value is this one. Okay, so R square is 0.99. Okay, when it is rounded, so it's 98. So 98. So let's put it for 4 digits. for R square. So 991. So which is again a good number. So here we can so here mean absolute error is actually 1.41, and this represents the average absolute difference between the predicted and actual performance index of the test data. A low value like this 1.41 and all less than 2, which is that is actually suggest a good agreement between the model's prediction and actual values. And similarly for mean square error, that is 3.17. This is actually measures the average square difference between predicted and actual values. Uh, this is a lower value, it is less than 5, and also it's comparatively with the scale of the data, it's very low. So it actually suggests a better model fit. While it's not directly interpretable with the numbers and all, it contribute to the calculation of RMSE basically. So we want take this one and discuss further about the model accuracy, but we will consider this for RMSE calculation. But here the RMSE value is 1.78, which is actually very less than 2, and this square root of MSE value actually provide the estimate of a typical error in the same unit as performance index. So this value is close to 2, suggests that on average models prediction will vary within 2 units, okay, with the actual performance index. So you can see here also it actually varies at least 2 units from the actual values, okay. So not more than that on an average. So that is what this model is saying, and R square is actually almost 0.99, and this is actually a very high R square value, which indicating the model is actually having a very good performance. Now we can mm, put the residual histogram. Okay, we will put the histogram of residuals. Okay, so we don't need to take this one directly. We can actually take the actual and this one. The difference between these two we can take. So here PDT is the data. Uh, PDT. Okay, so this will be the residual, and we can put a histogram like this. So histogram of residuals, and X level will be residuals, while color will be this and borders of black. So let's put that histogram. So this will be histogram. So I'll take more bins here for 20 breaks. Let's take because we have 100 samples, so we'll take 20 breaks at least. So this is the histogram. What if we take 30? That is a standard number we usually take. So this will be the histogram. Okay, this histogram also says that approximately normally distributed, not exactly, but approximately, because in real data we will only get these things. Now, yeah, so that is about the model, and if we wanted to predict, um, okay, so that is about the model part. So any questions here, or you can even come back after the break and we can discuss. So I will just share this one um, in the classroom or WhatsApp itself, so you can simply have a look while you are on break. Okay, now we will be moving to generalized linear model, and first we will see the Gaussian family because that is same as the linear regression model we have learned. So first of all, what is generalized linear model? Okay, so generalized linear model are extensions to linear regression. Basically, we can say like that. It's an extension to the linear regression to areas with where assumptions of normality or homoscedasticity did not hold. So, whenever we have linear regression or multiple linear regression models, that is having some um, issues with the assumptions of normality or homoscedasticity and all. So there we will be using the generalized linear model. So there are different versions of GLM models. Each are actually for different type and distributions of outcome. So the major GLM models are, first one is, as we discussed, that is the Gaussian model, generalized linear model with Gaussian family, Gaussian distribution. It's a normal distribution Gaussian. So that is actually the what we have seen with the LM function. Then we have logistic regression. Then Poisson regression is there. Then gamma distribution is there. Then binomial, negative binomial is there, and beta regression is there. So if we look at each of these things, logistic regression, that is for binary outcome. If we have some out continuous variable, or if we don't have a binary variable, we can convert that binary continuous variable in our model to a binary variable, and we can analyze using that variable. So we'll see an example with that today. And then um, okay, then logistic regression is for binary outcome like yes or no, correct or incorrect, or high or low. So those kind of things. Uh, it's a fantastic tool that provide useful interpretation information for a binary category. Much like simple and multiple linear regression, logistic regression also use some dummy coding and provide coefficient that tells us the relationship between the outcome and independent variable. Okay, but it's mostly a classification model. Since the outcome is binary here, we use the statistical information to make things work well. That is, this is actually make the outcome in a log odds method. So a simple exponential of the coefficient, and we get the very useful odds ratio. So that is a very common in many fields of the binary data when we are using. Uh, okay. So that is about the logistic regression. We'll see how we can perform a logistic regression. Then we have the Poisson regression. So in okay, so the difference in Poisson regression is the Poisson regression will be using a count variable as the outcome. Okay, outcome will be a count variable. So it won't be a continuous variable. Now then we have the gamma regression. Regression with gamma distributions are called gamma regression models, and they are often found very when the analyzing the cost in dollars and all the cost variables and all when it comes. There we commonly use the gamma regression, so it is more fit to the gamma distribution. So that's why it's very similar to the Poisson, but not require integers, and it can handle more dispersion. Okay, if the data is more or having more dispersion metrics, and also if it is more scattered, and also if it is dispersion values are very high, then we can simply use the gamma regression. Now then we have the negative binomial. So somewhat similar to the gamma, like negative binomial is for zero inflated count variables. It makes slightly different assumption than other Poisson or gamma, but it's more kind of uh, similar approaches we are taking. And then we have the beta regression. For outcome that are bounded between lower and upper bound, beta regression is actually used. Okay, so if you have some values that is bounded with upper and lower value. So for example, if you are looking at a test score that can be bounded between 0 and 10, sorry, 0 and 100. So like in here, so their beta regressions are very useful. Okay, that is a very flexible method for analyzing these kind of a variation. So we will see how we can perform these regression models for our data, and we will do the model comparison and evaluation using this one. Okay, then also we have mixed effect models and all. That is when we have some effect on some other things and all, so that we will discuss later, not in today's session, but we will discuss those in later stage. um, okay, in the next session we will be discussing the time series analysis, um, uh, first cut of time series analysis with some example data, and then we will be going with some of the mixed effect models and all, mixed how we can use the mixed effect models and all there. And then we will be checking the PCA, or dimensionality reduction things and all. um, so these kind of things, and just we will look at the Monte Carlo simulation on example for that. And then we will go to some introduction to machine learning and other features. So the machine learning also we will be looking some like regression model, how we can apply the regression model in machine learning terms, and then how we can do the support vector machine, random forest and decision trees, and cluster models and all. So these things will be seen machine learning. And yeah, that is what we have pending in our syllabus. So those things we will be discussing on upcoming session. So we have, I think, yeah, we have okay, 8 more hours to cover these things. So we'll try to do it within that time frame. Okay, so now let's move to the generalized linear model. So so okay. Okay, so yeah, so these are the different type of Gaussian sorry, these are the different type of models we have. Other than that, there are many. So we'll be more focusing on this thing for now. Okay, So we also have other models like binomial, quasi-Poisson, so etc. etc. is there. So those things we can think later. So first we will start with the GLM family. That is nothing but it is similar to the uh, multiple regression model we have seen currently. So okay, so here we are just trying to model the same data GLM model using the GLM function. R is having a GLM function, okay, that will handle the generalized linear model instead of this thing like linear model. So we will evaluate this model, GLM model. So the syntax is actually similar. Like instead of LM, we are using the GLM, and we are putting the method here, performance index against all other variables. Data equal to df. I'll use df itself, not df1. So then family. The only thing is we need to put family, which family we are using. Okay, so family is the error distribution and link function. Basically, it's a error distribution and link function, we say. Now, if we can say, okay, I'll put G for generalized Gaussian model. Okay, so let's check this model. Okay, here also we are getting the intercept values and all these things like okay, then okay, okay. So if I run this one. Okay, so I can see here like this is more kind of similar when it comes to this two models. So you can see the R square here and the R square. So the values here and also it's the coefficient and all are almost similar. Okay, so the coefficients and all is similar. Then the okay, so all these values are similar. You can see. Um, okay, so we can predict the values for total data, and then we can find the R square for this model. Okay, okay, so yeah, so here we can find the R square as well. So R square is also 0.988. That is actually what we have here as well. So it is actually similar. Okay, so all these values are almost similar. So we can consider this model, Gaussian model. So this is how we can put the linear regression, multiple linear regression using the GLM function. And then if we need any plots and all, we can actually do those things. Mm, okay, so we can do those things. We have already seen everything for the Gaussian, so I'm not going for the plot and all here. Then the second one will be this one, the GLM with Poisson family. So basically, we need a count data for this one. So that is how the Poisson regression will work. So But for the time being, I will be working with the performance index itself. It's an index value, so we can consider this as a count, because index in this is an index in um, integer format, so we can consider this as index itself. So the syntax is similar. GLM, performance index against other variables. Data is given. What is the data set name? And our family will be Poisson. So I can check the summary of the model, and yeah, I will be getting something like this. Now here, what we are mainly focusing. Okay, I'll remove the model here because we have already seen the model. So okay, here we have AIC values. Okay, AIC values are there. So here also we have AIC value. This AIC value we have here is mm, AIC value actually stands for the Akake information criteria. So Akake information criteria, it is a measure used in statistical model selection to assess the relative quantity of different model for a given data set. Okay, so this is actually a measure we use to compare different models in our modeling part. Okay, so when it comes to model 1, model 2, sometimes we need to perform multiple models, like one model won't be enough, or one model won't fit enough for the data. So we need to iterate, do some iterations and do for the multiple modeling, and also there we need to consider the AIC model, and we will compare the AIC model, and a lower AIC indicate a better balance between the model. So we will consider the lower AIC value models. Okay, so that is why we are using the AIC values for comparison of different models. Okay, so here, if you see the regression model, the AIC value is 42627, and here is 61412. Okay, with the Poisson model. So currently, with these two models, when we compare these two models, based on AIC, Poisson model is actually giving a better result. Okay, than what we have in the um, Gaussian model. Okay. Now we will see other models as well. So, okay. So we will see other models as well. Now we will look at the gamma model. So gamma model is basically uh, it need a continuous and positive data, but one condition is it's actually need a positive skew data. Okay, it's need a positive skew data. So our data is more kind of low, normal, but it is actually having some uh, this also. Okay, so here. Okay, here we are using the same syntax only, GLM model, performance index, and against all the other variables. Then data equal to data frame. Family we are giving gamma, and link function we will be putting log. Okay, normally in Gaussian model or simple linear regression model, the link function will be identity function. When it comes to Poisson, that will be log function. Okay, Poisson it the default will be log. When it comes to gamma, we have inverse or link function is there, log link function is there. There are multiple link functions. So here we are using the log as we already did it for the Poisson and all as per the data. So we are using the log as link function. So it will take the log of the target variable. Okay, so now if you see the models here, we are getting the estimates and all like this. So here also you can see it is having our studied is sorry. Um, okay, this is actually having more weights on this variable, our studied. Okay, hour studied, and then followed by sample questions. Okay, not the sample questions. So hour studied and previous questions, it's actually having more weight, but the weight is actually okay, here it is actually giving more weight to this particular one. All are negative, so this is 10 raised to minus 2. So it's actually giving more weight to extracurricular activities, then followed by our studied, then sorry, extracurricular activities previous score, then it is giving way to this one, and then sample question practice and sleeping hours. Okay, maybe because of it is a factor variable, it's giving more load to this one, so that we can investigate. So this is actually how this model is performing, and here you can see it is actually giving a lower AIC value as well. Now, okay, so here we have seen the gamma model. Now we will see, okay, so now we will see GLM with inverse Gaussian. Okay, so this is inverse Gaussian. So there also we can put this one like family equal to inverse Gaussian. So there in inverse Gaussian we'll be using the identity as the uh, okay, square root of it is no valid coefficient, set of coefficient has been found. Please supply starting value. Okay, okay, let's see in this one. Okay, so here the link will be inverse, so we can use the link equal to inverse here, and okay, so this model here we can see the coefficient and all, but here you can see this is actually having a very high AIC value, which is not a suitable model compared to other models we have performed here. Okay, now we can also check a Poisson sorry uh, logistic regression as well, but for that, okay, but we need to convert the predictor variable to a binary variable. So for that, we will convert if performance index is greater than or equal to 50, we will put 1. Otherwise, we will put 0. Okay. So after this conversion, we are creating this new variable performance binary, and then we can actually put this one. So I'll put df2 here. Okay, uh, df2, df, then I can put muted. Okay, so yeah, I'm creating a new data set here, df2, that is actually by performance binary I'm creating if else this condition, and removing that performance index variable, and I am performing the GLM model. So here my data will be look like okay, my data will be look like df1. Oh, okay, it should be df2. Okay, why it is not running? Okay, so df2 is there. So here we have created that performance binary that is based on the score. If it is greater than okay, existing value, if it is greater than 50, we will put 1, otherwise 0. So we got a binary variable there. Okay, so that is there. Now we can put the GLM model for this one. So and okay, so and we will put the family equal to binomial. So here we'll put the family equal to binomial. Okay, and okay, then summary of the logistic model. So we will be getting the summary here. So here the summary is actually a bit different. So we have all these things, and here you can see the AIC value is very low, but this is actually not saying that compared to other models this is actually good, because it's actually using an entirely different approach. Even though this value is very low, we cannot take this one because it's actually predicting it in a different scale. So we'll do one thing here. We have this one, but we'll do s dot factor, because we need a factor variable there. So I'll put this one. Okay, okay. So it will by default take it as a factor variable, but still here it's actually this one. So here if you look at this thing, here also it's actually saying our studied is actually having more impact than previous score. Okay, so ours studied actually having more impact than previous score. So that is actually what it is saying here. So similar input only we are getting from this one also, the gamma model as well. So there also it was saying the same. Our study is actually having more impact. So, sorry, there it was extracurricular activity, not this one. So here it is saying our study has more importance compared to previous score and all. Okay, now uh, we can also predict the values in logistic model. So there we can predict the GLM model, predict function GLM model, new data is gf2, type equal to response, and okay, response, and predicted class. So here what it will predict is, here what it will predict is, it will predict the if you look at here, the prediction, it will predict the log values only. So log values are it's actually predicting here. So based on these log values we need to create the predicted class. If else prediction log greater than zero point 0.5, our class will be 1, otherwise it will be 0. Okay, so we will be using that one. So our predicted class will be 0 and 1 for all the observation. Okay, now we will create a confusion matrix uh, using a table like predicted values, the actual values and predicted one. Okay, so we can see the confusion matrix. So actual and predicted. If actual is 0 and predicted is 0, that is this much, and this much is actually having actual value 1, but it is predicted as 0. Okay, now uh, again actual value is 0, and this is actually 133 is predicted as 1. Okay, actual 0 was there, out of that 133 is actually predicted as 1. So this is a false prediction. Now here actual was 1, but predicted was 0 for 124. Okay, so it is also a wrong prediction. Now these are the metrics we use for logistic regression to evaluate the model, not the R square. So accuracy, precision, recall, and F1 score. So that will be based on this confusion matrix. Okay. So accuracy will be diagonal sum of confusion matrix divided by sum of confusion matrix. Okay. So that will be our accuracy, and precision will be confusion matrix divided by sum of confusion matrix. Uh, okay, correct. Okay, I will write the formulas as well. Okay, accuracy is the ratio of correctly predicted observation to total observation, and re recall is the ratio of correctly predicted positive observation to all actual positive observation. So that is this one, and precision is the ratio of correctly predicted positive observation to the total predicted positives. Okay, and based on this actually we will call the F1 score. So here accuracy is sum of diagonal values of confusion matrix. So sum of these diagonal values, that is a correctly predicted one, divided by sum of the confusion matrix total observation. Now here recall is confusion matrix 2 by 2, that is these values it's taking. um, Confusion metric 2 2, that is in this value correctly predicted positive divided by this one, this total. Okay, so that is recall, and precision is confusion matrix this one, correctly predicted positive this thing divided by sum of this one. Okay, second column. Okay, so this one here it was first second row, and here it is second column. Okay, so now, and we will have the F1 score. F1 score will be 2 into precision and recall divided by precision plus recall. Okay, this is actually the F1 score. So now accuracy, precision. Okay, now I will write a few more things, that is true positive and false negative. Uh, we'll create a matrix for that. Okay. Okay, this is actually the matrix of the true positive and true negative. Then false positive and false negative. Based on this only, we are calculating the ac accuracy, recall, and all. So let me keep it outside. Okay, let me keep it outside. Let's put this as in markdown format. Give me a sec. Okay, so okay, so okay, so this will be the formula. So let's go to the visual part. Let's see. Okay, so this is the confusion matrix, like predicted and actual. So this is actually we can correlate this with the other one. Okay, okay, so we can relate it to this one. So here this it was actually zero and it was predicted as zero, so it is true negative. And it was actually zero, then predicted as positive, that is false positive. Now it was actually 1 predicted as 0, so that is false negative. Here it was actually 1 predicted as 1, so that is true positive. Okay, so this is how the confusion matrix look like. So this is the way the confusion matrix look like. Now based on confusion matrix, precision is the measure of accuracy of positive prediction, that is true positive divided by uh, true positive plus true false positive. Okay, so this way. Now recall will be true positive divided by true positive plus false negative. Okay, so F1 score will be true 2 times precision into recall divided by precision plus recall. Okay, so that is what we have done here. Okay, this is a formula for that one. So based on that, our precisions and recalls will be like this. Accuracy is 97 and precision will be 97. Recall is 97 and F1 score will be 97. Okay. Now I'll print the confusion matrix also here. Mm, okay. So our results are look like this for the logistic regression. Now we want to explain these values. So how each of the values are actually contributing. Okay, now we will focus on that one. So first one is confusion matrix, as we already discussed. Like this is the confusion matrix. How many true positive and true negatives are there, and how many true false negative and false positives are there. That is what explained by the confusion matrix. Okay, now the total observation we have is 10,000 from this one. So accuracy is 97.43 percentage. That is the 97 percentage of the models are classified correctly. Okay, so that is errors are very low in both sides. It is just 2.5 percentage errors in both sides. Now precision is 97.5 percentage. So that is when the model predict class 1, it is actually 97.75 percentage correct for predicting one value. Okay. Now recall or sensitivity, that is also 97.9 percentage. This is correctly identifies actual class 1. Okay, so that is actual class 1 is predicted with a 97.9 percentage of actual classes. Okay, so that is actually a good direction. Now the most important factor is F1 score, that is 97.83 percentage. That means the model has excellent balance between false positive and false negative. So this is the best signal metrics when we have a both false positive and false negative matter. So every every logistic regression that actually matter. So here we can see that there is some imbalance in the class is existing, like um, this many imbalance in each classes are existing, but that is a mild imbalance only. Okay, it's not a major one. So here false positive is 133 and false negative is 124, and so errors are very small, well balanced and all. So we can use this model. So this model is actually good. Okay, so here we don't use r square and all, so we don't need the r square and all for logistic model. So we can simply explain the um, accuracy, precision and recall, and also f1 score. So the conclusion will be we can say it in a conclusion way, like okay. So this confusion metrics are that the model perform exponentially well with the accuracy of 94.43 percentage, both in precision and recall is also high. That is indicating the model make very few false positive and false negative errors. The F1 score is actually really good, that confirm a strong balance between the precision and recall, and it demonstrating a high classification efficiency as well. Okay, so okay, so now we need to find the for logistic regression. We need to find some more parameters, that is the ROC and AUC. So okay, for logistic model we'll also use these things and these parameter to predict the model. So we'll be create that as well. So for that we need this library. So we keep it in the top as we discuss. Uh, let's keep it here. PROC. So let's load that package. Okay, so it's asking for installation. So I'll load the libraries once again. Now, okay. Now we'll plot the area under ROC curve and AUC. So here the okay, okay. So here okay, here this is the ROC curve and ROC curve. So and also it is show, we have calculated the area under this curve as well. So here while doing a comparison, AOC is actually 99.78 percentage. So that is extremely good. Most of the values are actually falls under this one. So a ROC curve actually represent the sensitivity in y-axis and you can see a specificity in x-axis. So okay, now diagonal line is actually showing the AOC this one and this is our model. Okay, this is our model how it is actually predicting this blue line the curve. The carve is almost vertically to sensitivity 1, so you can see here it's almost close to 1, so that is why we have 99 percent 97 something we got there. So and it is also flat at the top, so it actually tells you there is a high true positive rate and very low false positive rate. Okay, that is what it is actually saying. We have a high, very high positive true positive rate and very low true false positive rate. Okay, now AUC value is 99.78. That is, there is 99.78 percentage probability that the model will rank randomly chosen positive instant higher than a randomly chosen negative instant. Okay, so that is a perfect classification for this one. Um, as we already know, like these things now. Okay, so we already had these things like accuracy, these things, and let's put it in this way. Okay, earlier we had accuracy, precision, recall, and F1 score like this. Now we have this thing that is performance is robust across all the thresholds and not dependent on cutoff like zero point 0.5 and all. That is what the model is actually saying. Okay, so that is the interpretation. Like and this ROC curve for logistic regression model lies closed up to the top left corner, that indicating excellent discriminative ability. The AUC value of 99.78 confirm near perfect classification performance, showing that the model effectively diagnoses between two classes across the all the threshold. Okay, across all the threshold, it's actually giving this one. Okay. And also we can say there is a 99.78 percentage probability that the model will rank randomly chosen positive instant higher than randomly chosen negative instance. Okay, so that is the interpretation for AUC and ROC curve here. Uh, okay, so any questions so far? Any questions here? Please let me know if you have any questions, or else please put a comment like you don't have anything also, so we can close it out. We'll also put a PR curve as well. So PR is precision recall curve. So so for that we need PRROC function. So package. So we'll load that. Okay, that is there, and let's put this one. So okay, okay. Now this is the PR curve. So okay, this is the same thing. Like the PR curve is actually showing. Uh, if the classification is classes are imbalanced, then actually sometimes ROC curve can mislead the predictions and all. So that way we need the PR curve. So it's actually the opposite to ROC curve. Like ROC curve will have a left direction, and now we have a right direction. Um, and you can see here AUC values are 99.8 percentage for this one as well. So that is a very excellent one. So it is close to one. That is a good one. So we can actually conclude this one is a good model. Okay, so this is what we have for the logistic regression. So any questions here for logistic regression? If nothing, can anyone put a no at least in the chat? So this is just for I can make sure I am stay connected. Sorry. Okay, thanks. Yeah, perfect. Now, now we have several models, and we need to compare the numerical models. So I will just go to this. Before the logistic model is something different, so we cannot use a comparison of AUC there. So we'll be compare the models here. Okay, to find out the best model. So for comparing that one, we can AIC values, we can take it for all the models. So model names we are putting here. So okay, so we are getting the models here. So okay, so the AIC values will be okay, so these are the AIC values here for different models. So this is how, even if you are doing some tuning and all for the same model, same regression model also, we'll be comparing the model based on the AIC values only. So based on the AIC values, we will be comparing the models. Okay. So here we have this model. So uh, the lowest value is for a GLM Gaussian. So the AIC is actually 42,627. So uh, okay. So AIC value is basically okay. So okay, come here. Basically, the AIC value we have. Okay, this is there. So basically, the AIC value is actually minus 2 log likelihood plus 2k. K is the number of parameters. So that is actually the formula for AIC. And lower the AIC is actually considered as better the model. Okay. So okay. So this is actually the formula. AIC equal to 2 minus 2 log L plus 2k, and where L is log likelihood of the model and K is the okay, K is the number of parameters in the model. And also we say that lower the AIC value is actually a better result. It actually gives a better model. Okay. Now here um, based on our interpretation, so here the if we can let me rerun this one once again. Okay, so AIC thing. It is not showing everything. Okay, so these are the values we have. So comparing these values, GLM Gaussian is actually having a very low AIC. So GLM model is actually having a better performance compared to other models. So here GLM inverse Gaussian is having a very high model, so that we cannot consider at least. So here GLM Gaussian is actually having the best model across the models. We can go with that one. Um, so that is how we can interpret the AIC values from these one. So we can mention that also here, like okay, I'll copy this part on the top. Mm, okay, let me put it here. Okay, it should not be there. Okay, now we can put the interpretation here. So here, okay. So our interpretation will be like this: given the same predictors and the Gaussian GLM explain. Okay, it actually okay, it explains the data best fit with the least unnecessary complexities in GLM Gaussian model. So this is how we conclude a model as well. So any questions so far? So we have seen the multiple linear regression, uh, and some of the generalized linear models, and okay, yeah, so we have seen couple of the other models and all. So okay, so basically we started with the real data set, and we did some exploratory analysis and all. First we load the library and do some exploratory analysis and all. Then okay, let me take the PDF here. Sorry for that. Okay, so we take the data set, and then we have loaded the necessary libraries and all, and load the data set and explore the data set here. Then we did some variable conversions and all as needed, and here we found out some variables having some issues, so we updated the column names as needed. And we did the summary statistics and all, checked for the missing value, duplicate value, and remove the duplicates as well. Then we use the summary function to again get to know the data set. Then we did some exploratory analysis on a couple of the factors, and try to identify what are the needed values and all. So we did those things and all. Then we came with the histograms, and we check all the variables. So when we tried to box plot, actually one variable is actually standing alone. So we remove that, and then came with other box plot. So then there was no outliers in the data. So we plot the factor variable then, and also look at the factor table. Then we convert the extracurricular activities column or factor column to numeric one, and we created a pairwise scatter plot of all the data. So that doesn't gives us any fruitful information. So we choose the plot that is showing the linear relationship between the columns, and then we have gone through uh, these plot, and it gives us an idea like previous score is the factor that is giving more importance, or that is actually having a more linear trend with the predictor, and followed by our studied, and other variables are actually showing a very less impact. Now we see the correlation metrics and plot the correlation. So we can see only few of these things are actually having a correlation. Only two factors showing at least a decent performance. So we just updated the plot with some color palette and some updates. So we get a neater one plot. Then we test the normality for target variables. So we check the normality for a couple of variables, numeric variables, along with the target variable as well. So it is somewhat actually normal, even though it's not exactly normal. We try for the Shapiro test, but actually it failed because we don't have more than 5,000 observations, so it actually failed there, violate the condition. So then we went with the multiple linear regression model with LM function. So we use the formula target variable to all the other variables, and we find out this model, and we run the diagnostics and all. We check the VAF and all. So VAF and all the diagnostics actually satisfy the model. There is no much issues in the model. So we test the regression model with ANOVA also. So that also gives us the confirmation like the model is statistically significant. All the variables used are statistically significant. So we use the prediction option. We predicted the values in the same data set using a sample. So this method will be known as the in-sample method. So we use the in-sample method to do the comparison, actual and predicted value, and we use that to compare. We find out MAE value and RMSE value, and based on that we calculate the R square as well. So based on MAE and RMSE value, it is almost fine. That is less than, values are less than 2, so that is actually uh, it was actually good. Then we put the histogram of residuals as well, and then we move to the generalized linear model. So in generalized linear model, we have seen couple of models. So first we see the Gaussian family, that is same as the model we have. Like it is same as the linear model we have already seen. When we the values are very close to the actual value, then we check with the Poisson model, gamma model, and inverse Gaussian model. Then we cover the AIC values and all, and AIC confirms that the GLM model is actually having a better AIC value, so that is actually a better model. Then we check the logistic model. So logistic regression model, we convert the data into a factor, like the target variable we converted into a factor like a 0 and 1. We converted a binary variable, one converted into a binary variable, and then we perform the binary logistic model. So we got the statistics here, summary stat here with all the coefficients and other parameters, and then we try to predict the values, and we created the confusion metrics from the value. So we got the confusion metrics like this, and we evaluate the confusion metrics and find out that there is very less false predictions are there in the model. So we check other performance metrics as well, precision, recall, F1 score, and all. So from those things, we actually got a pretty good model in this data, and we confirm that with the ROC curve and all. And also sometimes ROC will be tricky, not for at least this data, because this data we didn't have some impact on point or some changes or variations in point 0.5 and also that is not a this is actually fine. So but still we did a PR curve as well, so PR curve also satisfies the same. So we got a pretty good model in the logistic model as well. So this is what we have covered so far, and any questions here? Any questions so far? Any portions we need to um, repeat or anything? Otherwise, we can conclude the session here.